how green is this black? Like there could be different shades of green. This is what we will try to evaluate. So there's a technology or there's an assessment methodology called life cycle assessment. I believe most of you are aware of. So when I say life cycle assessment, and if I go with the ISO definition, it basically means compilation of all the inputs, outputs, and potential environmental impacts of product system or a process. And this can be done for any system. Why do I do it? I do it because I would want to know how sustainable is a particular route. On the face value, bioenergy pathways can appear to be very green. On the face value, people are saying about this is green hydrogen, this is blue hydrogen, this is grey hydrogen, but how do they do that? They try to compile how the different inputs are coming during the life cycle of the product, what are the different emissions, and what if I dispose of the product after useful life, what are the likely emissions. This is something we try to quantify when I say life cycle assessment, and this is basically done by different ISO guidelines. So why did LC came in the first place? So bioenergy has a good role to play. LC as such was introduced in the year 2007 or so, when there was an OECD report which says biofuels is the cure worse than the disease. It was the biofuels who basically that propelled the science of life cycle assessment in the first place. So let's go with the structure of LCA. So how I'll proceed is I'll give you the complexities involved in LCA with respect to bioenergy, and then we'll try to study a few case studies with respect to biochar. So a typical life cycle assessment would have these 4 phases, which are called goal, scope, inventory, impact assessment, and interpretation. This is something that is necessary for an LCA. So many of the times you will see there are LCA studies that are carried out in a fast forward mode. They are only considering about impact assessment, missing about the other factors, but that should not be done. And the stages that could be plus or minus, but a typical stages for any product cycle will be extraction of the raw materials, manufacturing, use, and disposal. Why would you do an LCA? But tomorrow if you would want to go for carbon credits, this is the amount of carbon that you sequester. You need carbon credits. You come up with a product which says this is carbon neutral. How do you justify that? Just on the basis of your thinking because I have extracted so much carbon, or do we have some scientific basis for that? If you would want to go or apply for certain government schemes, again LCA. So this is where an LCA comes into play. So now let's try to understand what are the complexities involved. Now I am showing you here the LCA or the life cycle with respect to a generic biomass or bioenergy pathway. You would have the production of biomass. This biomass needs to be transported. You would have some kind of conversion process like acidification, pyrolysis, or other processes. There would be bioenergy production, and you would be using it. If you see the dark blue colored, these are the ones mostly used in an LCA. So majority of the LCA that you're going to come across in the literature are going to just comprise of these 4 things. A few would also comprise in the production of biomass feedstocks. Why is that a bit complex? Because when the production phase is going on, the biomass tends to take in a lot of CO2. This is also the time when you have the production or the use of fertilizers, insecticides, machines. That is somewhat a bit difficult to quantify, and people tend to overlook it. And a very few studies would look into the indirect effects of bioenergy, which means there was a forest land. I wanted to go with some kind of biochar production. I cleared the forest. So there was a carbon sink in the sum of forest, but because the land use changed, the other things are happening. So that is the indirect effect which many people might not account for. And this is also the reason why some people will say that biomass energy pathways are carbon positive, others say carbon neutral, then still another group says carbon negative. Then we also need to understand the difference between attributional and consequential LCA. When I say attributional, it means I'm just looking at the product system. When I say consequential, I am looking at the extended boundary. Suppose I am using bioenergy pathways. I am producing some kind of biochar. Now by the use of this biochar, the conventional pathways gets disturbed. Maybe the energy production is happening at a lower rate for which I am using bioenergy. Maybe the char is replacing some other fertilizers or some kind of other soil enhancers, and their supply chain is disrupted, because of which there could be indirect emissions. Very few life cycle assessments take that into account. Land use change. Another thing that people tend to overlook because this is very complex and it's not easy to quantify, but if you would want to see the effect of your bioenergy pathways, these are something that you should not overlook. Water use. This was a primary use why that report by OECD came up in the year 2007. That was mainly aimed at production of biodiesel, which tended to have a huge amount of water footprint. But bioenergy pathways as such have a huge water footprint. We should not be overlooking that, okay, we are going for a somewhat sustainable pathway which has lower carbon emission, but there could be other emissions. Water use could be one thing, and it becomes pertinent in a country like India, which is not very rich in terms of fresh water resources. Transportation and storage. When I talk about biomass, it's not available year-round in most of the cases. You would have certain harvesting seasons, and you need to take care how it is being harvested. If you are storing it, it would have methane emissions because the degradation is going up, and that methane has an effect of normally 25 to 30 times as compared to storage. If I talk about the transportation, most of it is again going to happen using diesel-based vehicles which have a lot of emissions. So we might not want to neglect it. If you are transporting biomass more than 100 kilometers or roughly 60 miles, the emissions from the transportation would be way more than the emissions from the other aspects of the bioenergy. A very important thing is the multiple products. Now suppose you are doing biomass pyrolysis and it's going to produce you bio-oil and biochar. Now, if there are two products, how do you bifurcate the emissions that are coming from the biomass supply chain into two things? One thing would be you allocate on the basis of the mass. So here is a unit process, any process was it, which is producing 20 kg of product A and 80 kg of product B. And let's assume that the total emission is 1 kg. So intuitive thinking goes that like the unit process or the product A should have 20% of the emissions, which is 0.2 kgs, and product B should have 80% of the emissions, 0.8 kgs. So far, so good. But what if this 20 kgs of product A has a market value of $900 and this 20 kg or 80 kgs of product B has a market value of $100? Now in case I would now want the allocation to be done on the basis of the market value, because even though a product is produced in a small amount, the market value happens to be large. And if I do an allocation of the emissions based upon the market value, you would see the results have interchanged. And this is something that we need to be consistent about when I do an LCA. Whether I'm doing a mass-based allocation, whether I'm doing an economic-based allocation, or a volume-based allocation. The ISO standard says like mass-based allocation should be given priority, but again different studies tend to adopt different kinds of assumptions which lead to different kinds of results. Finally, the question of biogenic carbon. How is the carbon different from biomass in case of coal? If I'm producing energy from biomass or producing biochar, both are taking carbon from the environment. The coal took it maybe millions of years back, the biomass just took it maybe recently, maybe 100 years back, 10 years back, or 1 year back. Ultimately, this carbon ends up into the atmosphere. So how are they different? It's a time frame. When I'm using coal, I'm emitting the carbon that had been captured in the form of coal for millions of years. Whereas for the biomass, the cycle was quite small. Now, if the cycle is small, should I take that to be nil? Again, a question of debate. Some consider that to be biogenic, it's carbon neutral. Others consider no, because that carbon is going to stay in the environment maybe for 1 year, 2 years, 3 years, 10 years, till it's taken back in the biomass cycle, there should be some emissions attributed to it. Others say no, it should be equivalent to coal. Some people say that burning of biochar or burning of biocoal is equivalent, because I'm not talking about what is getting sequestered in the longer run. So it's a matter of debate, but it has to do with how much time the carbon dioxide that is released from any bioenergy pathway is going to spend in the atmosphere. Let's try to now understand these concepts with the with the help of focusing on the biochar. Now, as we have understood in the symposium, like biochar production would have different pathways, different grades of pyrolysis, torrefaction, gasification, and even hydrocarbon carbonization. All would lead to different kinds of biochar and have different process conditions, which means the energy input that would have gone or the energy that would be needed in the process would have been somewhat different. Now, if I talk about this typical life cycle of a biochar, you would have different kinds of biomasses. Some could be farm-based, others could be coming from the forest, still others could be coming from the livestock, others could be coming from municipal solid waste or wastewater treatment plants. Now, all of this have different types of engrained carbon. All of this would have different kinds of energy value. Further, it would need different kinds of pre-treatment. Some of it might need some kind of storage, other needs a good amount of storage, still others might need pelletization or briquetting for their transportation. So once I have done that, I will take it to maybe a power plant or a conversion unit where biochar is getting produced. And this biochar then will go into different uses. Soil application could be one, then I believe in this symposium we have been discussing about different high-end applications of biochar as well. Again, what would affect the LCA? It's basically a type of feedstock. It's not that all feedstocks are created equal, because different feedstocks would have different amount of energy and carbon and different life cycles. The biochar production method, all of would have different kinds of energy input and biochar yield. System boundary, whether I am just considering biochar utilization or biochar production or the whole. The normal terminology that I use is cradle to grave, cradle to cradle, gate to gate. All of them are going to yield different kinds of results. And finally, end-use application. If I am just using it for burning, the CO2 ends up into the atmosphere almost directly. If I am using it for soil application, the carbon remains in the soil for pretty some amount of time. But again, that is also something that is different. Let's give you an example. Like this was a recent study that was done, and herein, like the authors were trying to produce biochar at different temperatures, different pyrolysis temperatures, 300 degrees, 400 degrees, 500 degrees. Now, based upon the temperature, the biochar yield is going to differ, and with different temperatures are also going to have different kinds of energy input, and they are going to replace the different amount of conventional fuel. The result is the amount of natural gas avoided would be very different in the three cases, because the different amount of energy is gone and different amount of natural gas which biochar is replacing has decreased. So the results are different. Another thing, so here the difference is given with respect to agricultural residue and forest residue. So AR basically refers to agricultural residues and FR refers to forestry residues. Now if you say with respect to agricultural residues, the climate change potential is almost the same as the temperature. It doesn't make much of a difference, because you are giving in more temperature during the production of biochar and the same amount of energy saved when you are replacing natural gas. But if you see the other factors like human toxicity, freshwater eutrophication as well as fossil depletion, they could be somewhat different. So this is one of the things that we need to remember, that an LCA doesn't primarily aim towards CO2 emissions. It also takes into account the emissions with respect to water, emissions with respect to air, emissions with respect to the human health, which are equally important. You might want to give different weights to it based upon your priorities, but an LCA as such is agnostic. It wouldn't give the weights. It's up to you to give different weights to the different priorities that you would have. Then, it could also all the CO2 emissions that come out from the different kinds of feedstocks. So herein you are looking at the difference between agricultural residues, forestry residues, and sewage sludge would have the different profile. Sewage sludge, if I'm using the sludge that is coming from the wastewater of the sewage treatment plants for the production of biochar, would have the biogenic carbon to a lesser extent. The normal assumption that is taken is 70% of the carbon is biogenic and 30% of the char is coming from the different processes that would have led to the production of char in the first place. So you see, if we compare the results of agricultural residues and forest residues, again there are negative emissions because of carbon emission, which happens to be lesser in the case of sewage sludge. So the total emissions from biochar production from sewage sludge happen to be somewhat higher as compared to agriculture or forest. Another example. Now suppose I am also considering different kinds of applications as well as the different feedstocks. So herein the biochar could be produced from corn straw, waste wood, livestock manure, and sewage sludge. And you can see that there would be different kinds of emissions that are occurring during the biochar feedstock preparation, biochar application, and biochar carbon sequestration as well. So it's not that every feedstock is going to have a similar kind of carbon footprint, and this is why it is important that if you would want to study the sustainability of your own biochar, you study that with respect to the biomass feedstock that you got it, and also the conversion process that is at hand. Again, the system boundary. I'm just giving an example that is again coming from a recent study, which are producing biochar from pyrolysis of biomass or sewage sludge and using it for some kind of agricultural or soil enhancement application. If I'm just considering till the production of biochar, I'm starting from the dewatering of the sludge till the biochar production, which is given in the box which has been marked in purple. there is a certain amount of CO2 emission that is coming from this process, maybe 25 kgs of CO2 per ton of biochar that is produced. I can have even a simpler system boundary wherein I am not concerned about this sludge dewatering or drying. I am just considered about the pyrolysis. The dried sludge is available to me and I am producing biochar. That's system boundary 1, given in the blue color, even lesser CO2 footprint. If I extend the system boundary, again there is a reduction in CO2. Why? Because now the char has been used in the agricultural field and it is a bit of it has been sequestered as well, which was not counted in the earlier two system boundaries. So just showing you the example, what the effect of system boundary on the overall carbon footprint of a biochar energy. Then application. Suppose I am using sewage sludge again, pyrolyzing it, producing biochar and using it for different applications, maybe agriculture, horticulture and co-incineration, where I am just burning the biochar for some kind of energy application. Just based upon the use or end use of biochar, the total footprint would be a bit different. If I am using for the agriculture pathway, what I am doing is basically more effectively utilizing the fertilizers that would have been put. So the reduction comes in the avoidance of fertilizers. If I am talking about horticulture, I am avoiding the peat moss which is normally coming from wetlands, which happen to be carbon sources as well. In that case, even more reduction in carbon and the GW happens to be on a lower end. For incineration, I am just avoiding coal, so the emissions reduction is not much. But even on the basis of end product, there could be a wide range of the CO2 emissions that can occur. Finally, I would like to end my presentation with the help of dynamic life cycle assessment. So this is something that is being explored in the recent years, where we want to see or bring the time scale to LCA as well, which becomes pertinent in the cases of biochar, because the emissions for soil application would be released over the time. It's not released in one go. If that accounting is also done, that how much emissions are released today, how much are released maybe next year, how many 10 years down the line, it gives us even more concrete results and helps us to make even better decisions. So the latest LCAs that are being done with respect to biochar application are with respect to dynamic LCAs, where the temporal aspects are also brought into place. So with this, maybe I can bring this presentation to an end. So this is just to give an overview why LCA is important. It helps us basically determine what is the carbon saving potential or the CO2 reduction potential or so-called sustainable pathway. It helps us to make scientific claims and also compare our products with other products or other methodologies for the production of biochar. So with this, I would like to end the presentation and I'll be happy to take any questions. Comparison is something that is tricky in that case.
No, if you use the biomass of the hectare, the comparison is much easier.
Yeah, but that gives you only on the biomass basis, not on the biochar basis. So if you're comparing biochar, that might be a bit tricky, in my opinion.
Yes, but in my opinion, the key point is you want to compare the environmental impact of different scenarios.
If you are just concerned with the biomass, that works well.
Because you want to valorize something.
That works well.
Okay? Okay, thank you. The question? Okay, so let's thank you again and congratulate Pratham. Thank you.
Long live India and France friendship.